Tema, Penerokaan unsur dalam alam, Bidang pembelajaran 8.0, Unsur dan bahan, Standard kandungan 8.1, Asas Jirim, Standard pembelajaran 8.1.1, Menerangkan dengan contoh bahan atom, bahan molekul dan bahan ion. Hasil pembelajaran: asas jirim, fokus, jenis bahan dan juga unsur. Saksikan video berikut. Video pertama.
Stated Clearly presents What is an atom and how do we know? Atoms are the fundamental building blocks of chemistry. Just like baked goods are made of a collection of different types of ingredients, matter itself is made of a collection of different types of atoms. Scientists have discovered 118 kinds of atoms, which we call elements. You can find them laid out on a chart called the periodic table. All things from the screen this video is displayed on to the eyeballs with which you're watching it are made of atoms, but a single atom is so small it is impossible to see with the naked eye. So there you have it. A random voice from a video you found on the internet claims that everything is made from invisibly small atoms. You may now blindly accept this as fact and happily move on with your day, right? No? Now you are extra curious? You want to know for yourself exactly why it is that scientists think they know that atoms exist? Well, to find out we must travel back in time to ancient Greece. Meet Democritus, the man that many historians credit for first clearly proposing the idea of an atom. In his day, it was thought by some that if you were to chop up a piece of matter, an apple for instance, you could just keep on chopping forever and ever. There was no end to smallness. For reasons not fully agreed upon by historians, this concept did not sit well with Democritus. Instead, he insisted that at some point, you would reach particles so small and so indestructible they could not be divided any further. He called them atomos, or atoms, which means uncuttable. Now, Democritus didn't actually have any evidence to back up his claim, and because of that, many people simply rejected it. After all, that which can be asserted without evidence can also be dismissed without evidence. Let's fast forward several hundred years and hop on over to the Arabic world. You probably know that salt can be extracted from seawater by simply letting it evaporate or boiling it dry. People have been doing this forever, but alchemist Jabir ibn Hayyan and those that followed his work took the science of extraction to a whole new level. Through careful experimentation, they developed complex processes of filtration, boiling, vapor collection, and cooling. They found that crude starting materials could be divided into multiple incredibly pure substances. Pure meaning they appeared to be consistent all the way through, unlike the complex mixtures of matter often found in nature. In the 1700s, a French husband and wife scientific duo, Marianne Poltz and Antoine Lavoisier, studied and built upon the work of their Arabic predecessors. They found that certain pure substances could be broken down even further through chemical reactions. Water, for example, can be boiled into steam, which is still water, but it can also be split into two pure gases, hydrogen and oxygen. No matter how hard the couple tried, however, they could not reduce oxygen or hydrogen into simpler gases. They concluded that the gases must be elements, foundational substances that cannot be created by mixing other chemicals together and cannot be broken down any further. With this concept in mind, scientists everywhere began searching for and listing as many elements as they could, eventually discovering all 118 listed on the modern periodic table. Some, such as oxygen and hydrogen, are gases at room temperature. Others are solids, such as elemental carbon and gold. Others still are liquid at room temperature, mercury and bromine. It was also found that under the right conditions, pressure and temperature, certain elements will react with each other upon mixing to form new substances with new properties. These are called compounds. The elements oxygen and iron can react to form a brown powder known as rust. Oxygen and mercury react to form a toxic orange powder. Oxygen and hydrogen react to form a clear, refreshing liquid. You probably know it as water. Though the steps may be complicated, all of these reactions can be reversed. Elements can be reseparated, and the amount of each element we get back after separation is always exactly equal to the amount that had reacted to form the compound in the first place. Wonderful. Elements are real, and they appear to be essentially indestructible, but what are they made of? If you were to zoom in on one, a chunk of pure gold for example, can you just keep zooming in forever and ever, seeing nothing but pure gold for infinity? In the early 1800s, a school teacher from England named John Dalton grew fascinated with chemistry. Along with conducting several experiments of his own, he read about every experiment he possibly could, paying special attention to the quantities of each element used up in every chemical reaction. In these numbers, he was surprised to find a pattern emerge. When two elements can react to form multiple types of compounds, they always do so in small, whole number ratios. In this example here, we see that in order to transform a gram of carbon into pure carbon monoxide, we need to add 1.33 grams of oxygen. To turn a gram of carbon into pure carbon dioxide, we need to add exactly twice as much oxygen. That's 2.66 grams. This, and many other similar observations, strongly suggest that oxygen and other elements are made of tiny, indivisible units. Atoms. He didn't know exactly how small an atom was, but the numbers suggested that the atoms of a single element were all nearly identical in size to each other, but different in size to the atoms found in other elements. In 1808, he wrote a 560-page book that briefly mentioned his discovery. It even came with some quite beautiful drawings. While scientists weren't fully convinced that atoms were real, they did find the concept of atoms extremely useful. It helped them make accurate predictions and perform cleaner chemical reactions. In 1905, Albert Einstein, in 1905 he was quite a bit younger than that. There we go. In 1905, Albert Einstein proposed an experiment and produced an equation that could be used not only to confirm the existence of atoms, but to determine exactly how big they are. A few years later, French physicist Jean Perrin, or I guess in French that would be something a little more like Jean Perrin, used Einstein's concept to actually do the experiments confirming beyond reasonable doubt, at least to other physicists and mathematicians, that atoms do in fact exist. Now, if you happen to love math and possess an in-depth understanding of physics, then great. You can just turn off this video right now and go read his book. But for the rest of us, a little visual confirmation that atoms actually do exist would be nice, right? Unfortunately, individual atoms are far too small to be seen with normal light. The wavelength of light is just too great. This means that normal microscopes cannot see atoms. In the 70s, a group of engineers led by Gerd Bennig and Heinrich Rohrer began working on what they called the scanning tunneling microscope, a microscope they hoped would let us take undistorted images of many different types of atoms. It uses a process called electron tunneling to scan and essentially feel the surface of the sample, much like you can feel around in the dark to get a picture of your surroundings. This is an actual scan of silicon atoms forming the surface of a crystal. The colors here are artificial, but this is real data showing the actual pattern of silicon atoms arranged in the sample. Later work by Dr. Wilson Ho improved the technique and cleaned up the presentation of data. While, quote, feeling the atoms does give us good information, researchers still wanted more. A group led by Dr. Ara Apkarian of the National Science Foundation's Castle Research Center discovered a way to use actual light to see atoms. In the past, this was thought to be impossible because the wavelength of light is so much larger than an atom, but by shooting light at the tip of a probe in a modified scanning tunneling microscope, they were able to essentially shrink the light's wavelength and get it to scatter off the sample onto a detection screen. By moving the sample bit by bit, hitting it with light again each time, they were able to piece together this image of a single nitrogen atom, each pixel representing an individual data point from the scan. If we smooth it out, sharpen the edges, and change their chosen color scheme, it is shocking to find how close John Dalton's old drawings actually were to reality. Our species has finally done it. Over 2,000 years after Democritus first proposed the idea of an atom, we have now received direct visual confirmation. Atoms exist. So in summary, what is an atom? Atoms are the fundamental building blocks of chemistry. How do we know they exist? Through chemical reactions, we can witness their effects. Through mathematical equations combined with indirect observations, we can calculate their various sizes. And finally, with the aid of new technologies such as the scanning tunneling microscope, atoms can now be seen. While the word atom technically means uncuttable, we'll see in the next animation that atoms actually can be split apart. Atoms themselves are made of smaller pieces. I'm John Perry, and that's how we know that atoms exist, stated clearly. Well, folks, there we have it. That was the first animation in my 4-part series on the basics of chemistry, the fundamentals of chemistry. Hope you enjoyed it. If you did, subscribe to this YouTube channel and click the little bell icon. That makes sure that you'll see the next animation when it comes out. Again, there's 3 more to go still, so make sure you're subscribed. This animation was funded in part by the Castle Research Center. CASTLE, that stands for Chemistry at the Space-Time Limit. This is a research group over at the University of California, Irvine, that does atomic and molecular imaging. They take pictures of atoms and molecules. When they're not busy taking pictures of atoms and molecules, they do science outreach. They fund projects like this animation that you just watched. And they also produced recently a video game called Bond Breaker that is absolutely wonderful. It will teach you the basics of chemistry and a little bit of nuclear physics. It's totally free to use, to play, to download. You can use it on your phone, you can use it on your computer, you can use it on your tablet. So go check that out as well. There is a link down in the video description. This animation was also funded in part by my patrons over on patreon.com/stated clearly. If you would like to join these wonderful people right here in supporting this YouTube channel, I would greatly appreciate that. These folks are awesome. So long for now. Stay curious.
Apakah maklumat yang anda perolehi daripada video tersebut berkaitan atom? Bincangkan bersama rakan dan guru anda. Input pertama. Bahan atom terdiri daripada atom sahaja, melibatkan semua jenis logam dan gas nadir. Contoh-contoh bahan atom. Contoh-contoh logam: kuprum, emas atau aurum, timah atau stanum, perak atau argentum, zinc. Contoh-contoh gas nadir: argon, gas yang paling panas; xenon, gas yang paling terang; lain-lain gas nadir: helium, neon, krypton. Video pertama.
Stated Clearly presents What is a molecule? Though textbook definitions of the word molecule can sometimes be a bit complicated, a molecule can be loosely thought of as a group of atoms stuck together, usually through chemical bonds. Here we see a single hydrogen atom traveling through the cosmos. It's made of one positively charged proton in its nucleus and one negatively charged electron. If our lone hydrogen atom happens to pass close enough to another lone hydrogen atom, their electrons, which are attracted like magnets to protons, can pull the atoms toward each other until they collide and stick together. The two atoms now share each other's electrons in what is called a covalent chemical bond. What were once two individual hydrogen atoms have now formed a single hydrogen molecule. This bond is not permanent. With enough heat or due to interactions with other molecules, the hydrogen atoms will readily separate once more. Different types of atoms can form different numbers of chemical bonds. A hydrogen atom can only form one covalent bond at a time. If a third hydrogen atom were to collide with a hydrogen molecule, it would simply bounce off, or, if it hits hard enough or in just the right place, it can trade spots with one of the existing atoms. An oxygen atom can typically form 2 bonds. A carbon atom can make 4. An argon atom won't usually bond with anything. Even though possible bond numbers per atom are pretty small, huge molecules can form if bonds happen to be properly arranged. For example, even though hydrogen can only form 1 bond, a standard water molecule is always made of 3 atoms. This is possible because oxygen, which can form 2 bonds, forms just 1 bond with each hydrogen atom. A single molecule of the sugar known as glucose is made of 24 atoms, a special arrangement of carbons, hydrogens, and oxygens. A typical fatty acid in the human body may vary in length. This one here is made of 38 atoms. And finally, a single protein, depending on the type, can contain over 500,000 atoms all covalently bound together. The molecular models that I've been showing you here so far are what we call space-filling models. They show us roughly what the outside of each atom's electron cloud looks like, and different types of atoms have been assigned different colors. When we look at real molecules with a scanning tunneling microscope, they look pretty similar to these space-filling models, but the atoms are not color-coded and their edges are fuzzy. That blur is partly due to the microscope's limitations, and partly because atoms actually do have soft boundaries. When looking at complex molecules, space-filling models, and especially actual images of real molecules, can be a bit confusing to look at. Which atoms are bound together, which atoms are just close to one another. For this reason, chemists sometimes use what are called ball and stick models. These highlight the bonds between atoms, the skeleton of a molecule, instead of showing each atom's outside surface. In 2009, Dr. Leo Gross and his team at IBM discovered a way to take actual skeletal pictures of molecules. This is not a drawing, this is not a computer-generated model, this is an actual scan of a real molecule. Amazingly, atomic theory was allowing scientists to draw molecules with surprising accuracy over 100 years before this image was finally taken. That's quite a testament to what good scientific theory can do. When atoms come together to form a molecule, the molecule vibrates between its bonds in a regular pattern. You can think of the bond as a bouncing spring. This is because the protons in the nucleus of each atom repel one another, while the shared electrons in each bond pull the atoms back together. The vibrations we find in molecules are the result of a perpetual tug-of-war between these two forces. If you add more energy to a molecule with heat or light, the amplitude, the length of each vibration will increase without changing how frequently each vibration completes its cycle. This means the bouncing spring stretches further and the atoms move faster. If you add enough energy, the bond will eventually break. Scientists are fascinated by molecular movements and want to understand them better. These vibrations have a huge number of potential applications in chemistry, medicine, electronics, and computer engineering. Watchmakers, for example, use the unchanging speed of molecular vibrations to build watches that keep nearly perfect time. In a quartz crystal, bond vibrations between its atoms resonate, causing the entire crystal, when cut to the right size and shape, to oscillate microscopically at 32,768 times per second. Inside each quartz watch is a tiny crystal along with electronics that can count the crystal's vibrations. This then tells the second hand precisely when to move. In April 2019, in the journal Nature, Junhee Lee and his colleagues from the Center for Chemistry at the Space-Time Limit have published the first images ever taken of molecular vibrations at the atomic scale. Though these images may seem a bit strange to you and I, they show researchers exactly how this molecule bends and pulses between its bonds. Scientists can use images like this to build accurate models predicting exactly how different molecules will behave under various conditions. With this new precision knowledge, engineers are working on solar panels that generate far more energy, computer chips that do not overheat, and researchers are planning to use this imaging technology to better understand our own DNA. Even in a field as thoroughly studied as chemistry, the old saying is still true. Somewhere, something incredible is waiting to be known. So in summary, what is a molecule? A molecule can be described as a group of atoms stuck together through chemical bonds. Different types of atoms can form different numbers of bonds. Molecules can be as small as 2 atoms stuck together, or, as is the case for some proteins, they may contain over 500,000 atoms all covalently bound together. Recent advances in molecular imaging are now letting us take snapshots of molecular vibrations at the atomic scale. I'm John Perry, and that is a molecule stated clearly. This animation is part of an Intro to Chemistry series sponsored in part by the National Science Foundation and the Castle Research Center. That's Chemistry at the Space-Time Limit. It was also funded in part by my wonderful supporters on patreon.com/statedclearly. Thank you, I could not do this without you. Along with this video series, Castle and the National Science Foundation have funded the creation of an amazing online video game called Bond Breaker. In the game, you are a proton, and you go on a bunch of little adventures, learning powerful concepts in chemistry and nuclear physics as you go. I've shown you clips of the game before, but a new version was just released and it is wonderful. Go check it out at testtubegames.com. There is a link down in the video description. Not only will it teach you new things about chemistry and atomic physics, it's also almost too fun to play. Today I went to play it for just a few minutes so I could record my screen and show you what the game looks like, but I ended up playing for over an hour, so kudos to Andy at Test Tube Games. You have done an amazing job. Teachers, use this in your classrooms. It's free.
Bahan molekul. Bahan yang terbina daripada 2 atau lebih atom yang sama atau berbeza atau kombinasi yang sama atau berbeza atom. Ia merupakan zarah yang paling ringkas. Contoh-contoh bahan molekul. Contoh molekul terbentuk daripada jenis atom yang sama, iaitu molekul gas oksigen, kedua molekul gas ozon. Molekul terbentuk daripada jenis atom yang berlainan, iaitu karbon monoksida dan karbon dioksida. Video ketiga.
In this lesson, we will learn about what ions are and how they are formed. When an atom gains or loses electrons, they develop a charge. Recall that electrons are negatively charged, so the gain or loss of electrons will create a charge. These charged particles are called ions. When an atom loses electrons, they become positively charged. Positively charged ions are called cations. An easy way to remember this is to recall that cats have paws. When an atom gains electrons, they become negatively charged. Negatively charged ions are called anions. Let's look at sodium as an example. Its electronic structure is 2, 8, and 1. It has 1 electron in its valence or outermost shell. When sodium loses this valence electron, it becomes a positively charged sodium ion. This charge is written as a superscript when writing the symbol. When drawing the electronic structure, enclose it in square brackets and write the charge on the top right-hand corner. Now, let's look at oxygen as another example. Its electronic structure is 2 and 6. Therefore, there are 6 electrons in its valence shell. Oxygen gains 2 electrons to form a negatively charged oxide ion. Remember to include the charge when writing the symbol and when drawing the electronic structure. If we look at the electronic structure of these 2 ions, we will see that they have a complete outer shell. We will also see that they have the same electronic structure as that of a noble gas. The sodium ion and the oxide ion have the same electronic structure as a neon atom. How are you feeling about ions? Are you ready to form ions on your own? Let's try. Please pause the lesson and draw the electronic structure of a calcium ion and a chloride ion. The electronic structure of calcium is 2, 8, 8, 2. It loses 2 valence electrons to form a calcium 2+ ion. The electronic structure of chlorine is 2, 8, and 7. It gains an electron to form a chloride ion. These 2 ions have the same electronic structure as an argon atom. Did you get the structures right? And did you remember to specify the charges? What do sodium and magnesium have in common? They are both metals, and metals lose their valence electrons to form cations. Group 1 metals, such as sodium, have 1 valence electron, and they lose this electron to form ions with a +1 charge. Group 2 metals, such as magnesium, have 2 valence electrons, and they lose these electrons to form ions with a 2+ charge. Oxygen and fluorine are both nonmetals. Nonmetals tend to gain electrons to form anions. Oxygen is in group 6 and has 6 valence electrons. It gains 2 electrons to form an ion with a -2 charge. Fluorine is in group 7 and has 7 valence electrons. It gains 1 electron to form an ion with a -1 charge. Group 3 elements, such as aluminum, lose 3 electrons to form ions with a +3 charge. Group 5 elements, such as nitrogen, gain 3 electrons to form ions with a -3 charge. Group 4 elements, such as carbon, tend to form covalent compounds. Stay tuned. In conclusion, an ion is a charged particle formed from either the gain or loss of electrons. A positively charged ion is known as a cation, and a negatively charged ion is known as an anion. The ions formed have the same electronic structure as their nearest noble gas.
Bahan ion. Gabungan bahan yang terbentuk antara atom logam dengan atom bukan logam. Ia dikenali sebagai sebatian ion. Contoh-contoh bahan ion. Pertama, natrium klorida. Kedua, kuprum 2 oksida. Analisis kepelbagaian bentuk unsur. Atom oksigen atau unsur oksigen. Apabila 2 atom oksigen bergabung, ia menjadi gas oksigen, bentuk molekul. 3 atom oksigen bergabung menjadi gas ozon, bentuk molekul. Atom ferrum. Logam ferrum terdiri daripada atom-atom ferrum. Atom ferrum dan atom oksigen. Proses pengaratan berlaku kerana ion ferrum yang terdapat di permukaan kereta telah bertindak balas dengan ion oksigen. Ia menjadi ferrum oksida. Hidrogen dan oksigen. Gabungan dua unsur iaitu dua atom hidrogen dan satu atom oksigen, ia akan membentuk molekul air. Rumusan. Definisi atom. Pertama, atom ialah zarah yang paling kecil di dalam sesuatu unsur. Kedua, atom ialah unit paling asas dalam unsur. Definisi molekul. Pertama, molekul ialah gabungan dua atau lebih atom secara kimia. Kedua, molekul boleh terdiri daripada gabungan jenis atom yang sama atau berbeza. Definisi bahan ion. Pertama, ion ialah zarah-zarah yang bercas sama ada positif atau negatif. Kedua, penghasilan ion berlaku apabila sesuatu atom menderma atau menerima elektron. Penilaian. Kenal pasti bahan-bahan berikut. Adakah ia bahan atom, bahan molekul atau bahan ion? Gambar pertama. Emas 999.9. Gambar kedua, gas nitrogen. Gambar rajah ketiga, zinc sulfat. Apakah takrifan sebenar bagi bahan atom dan bahan ion? Bincangkan bersama rakan dan guru anda. Sekian, terima kasih. Sampai jumpa lagi.